reason that we defined logarithms, namely doing algebra involving exponentials. Let's try to solve logarithmic equations. We have algebraic rules that we might be able to take advantage of. And let's start by even just listing those logarithmic rules. Yeah.
I don't think we've got that down,
No, you haven't, because they're right here. Get these out. And if anyone just didn't give me their review because they did something silly like left it at home in their dorm room, talk to me right after class and I'll tell you when you should turn it in. Ideally by the end of the day, if you haven't already. So let's start by just recalling logarithm laws. And one of them I think is already written on the board. A few of them are already written on the board behind me. Let's start by just thinking about translating between log form and exponential form. If someone writes down log base b of x is equal to y, how can you translate that into an exponential equation? You would.
Isn't y to the power of b equals x?
Almost. It's b to the y equals x. So you should think this b in the subscript of the logarithm, that's the base. And the b in the base of the exponential is also the base. So when you translate from logarithmic form to exponential form, you still have the same base. You just change from logarithm to exponent. What's the log base b of 1? 0. What's the log base b of b? 1. What does log do to multiplication? Turns it into a sum. It adds them. That's the log base b of x plus log base b of y. What does log do to division?
Subtraction.
Turns it into subtraction. Log base b of x minus log base b of y. What does log do to exponentiation? That power becomes a multiple, so it's y multiplied by log base b of x. We have the ability to rewrite any logarithm as any other logarithm. What is the log base a of x the same as? It's almost the same as the log base b of x, except what are we off by? Log base b of a. So one application is if your calculator, say, only knows how to walk base 10, then you can rewrite any logarithm as the log base 10 of x divided by the log base 10 of a. Or if your calculator only has an ln button, that means you can do any logarithm you want by just doing that. And I think there were a few people who were convinced that their calculator could only do log base 10. There were a few, right? Chances are you're wrong. I bet that if you look in your calculator manual, which is probably online, it does, because it would be easy to implement. You just need to divide. Finally, let's talk about the change of basis formula for exponents. If you're walking over an exponential with a base other than the base you want to walk in, you don't need to walk over that base. A to the power x is the same thing as b to the power x, except you're off by a little bit. You're off by the log base b of a in the exponent. People feel okay? So all I want to do today is a whole mess of applications of these rules. I want to solve some algebraic equations involving logs. And then what will we do? Well, I'll say, well, we're really interested in logs and exponentials because they model things that grow or decay proportional to the number of things there are. And one thing that has the property is radioactive elements. The more of a radioactive quantity there is in your collection, the faster it decays. We'll do a quick couple of examples thinking about radioactive decay, and as a consequence, studying carbon dating, because that's just built on top of the fact that you know how radioactive elements should decay. Finally, we'll do a few more involved examples by thinking about, well, we thought about logs so that we could solve things involving exponents. Let's solve things involving exponents. So there's the outline of today. So in some sense, there's no new content. I just want to do some algebra. That seems pretty nice, right? So today should feel pretty light. Gesundheit. And I mean, I'll also go through this. I'll give you guys lots of opportunities to say that it's time for me to be quiet, and you're just going to do it. But maybe the first one, I'll talk through it all together definitely. Let's solve the equation. The log base 3 of 3x plus 5 is equal to negative 1. What would you want to do to that?
Rearrange it to exponential form.
Put it in exponential form. That seems helpful. Right? The complicated stuff is all on the right-hand side. Nope, all on the left-hand side. So we'll make the right-hand side more complicated by making it exponential, but that won't be so bad. And then the left-hand side, the bit that has the x, will become simpler. So if you rewrite in exponential form, I know I have enough space to write 1, so I'm writing 1. You'll get 3x plus 5 is equal to 3 to the power negative 1. I mean, maybe you could say that's the same thing as a thought if you like fractions better than exponents. Does that look like an easy equation to solve now? Probably, right? It's linear. So let's go through it. So on this side, I see 3x plus 5, so maybe I need to subtract 5 from both sides. 3x is equal to 1/3 minus 5. I would like to get a common denominator to subtract them fractions. So 3x is equal to 1/3 minus 15 over 3. 3x is equal to negative 14 thirds. Did I do that correctly? It's a little bit small and the lighting isn't great. Let's see if I can make that better. There. Better? Yeah. Okay. Nice. So what do I still need to do to solve that for x? Divide the 3 over to the other side. Division by 3, that's the same as multiplication by 1 over 3. Either way, that's where you wind up. People pretty happy with that? So, what's the payoff there? As long as you have an equation that's honestly an equation in log form, and the stuff on the right-hand side of the equation is just like a constant, you can rewrite it in exponential form, and your life will become better. Let's try that again. Let's solve the equation. 2 times the log base 4 of x plus 1 minus 2 is equal to the log base 4 of 2. And I don't know, let's see if we just look at the remaining 3 equations on this page. Do you guys think you all know how to solve those already? Anyone? Well, let's see. Does anyone want me to keep talking through one more complicated example? Nice. So, I guess we'll start at the top. So there is an equation to think about. Is that an equation that's in log form right now? Not quite. There are a bunch of logs in it, but it's not literally log base 4 of thing is equal to that. So let's try to rearrange it so that we can do that. So in fact, let's let's start by doing this. I think I want to do this in a slightly different way. Do you know a number which 2 is the log base 4 of? Let's try to rewrite this 2 as log base 4 of something. And let's go aside to do it. Log base 4 of what equals 2? Yeah, so let's find out. So there's an equation in log form. Let's rewrite it in exponential form. Question mark is equal to base to the power 2, 16. So let's use this fact to rewrite that. So this becomes 2 times the log base 4 of x plus 1 minus the log base 2 of 16, nope, log base 4, it's all log base 4, equals log base 4 of 2. So now everything is at least log, yeah.
I thought on the right side of the equation, we have log base 4 of 2. I thought that was 4 to the x power equals 2.
Ah, so no, I was trying to replace this 2 with something else.
Oh, gotcha.
So my goal was, well, I would rather everything have a log in it because then I can use log laws.
Oh, I gotcha.
So, all right. So I wasn't trying to rewrite the log base 4 of 2 at all. I was happy with that one for the time being. So now, if you look at the left-hand side of that, could that be rewritten in terms of a single logarithm? Yeah. And maybe you would want to do it in 2 steps. I'll do it in 2 steps. Maybe you would want to do it in 1. So first things first, I guess that 2 can move up into the exponent, becoming the log base 4 of x plus 1 squared. And then leave everything else alone. Happy enough? So on the left-hand side, I now see a log minus a log. What is log minus log the same as?
Dividing.
Yeah, a single log with division. So that'll be log base 4 of x plus 1 squared over 16 is equal to the log base 4 of 2.
Do you mind switching it over to left?
Yeah.
Thank you.
Cool. Well, now it's definitely an equation in log form, so we could rewrite it in exponential form. But it's kind of even better than that. Do I see log base 4 of something is equal to log base 4 of something else? Is log a one-to-one function?
Mm-hmm.
So the only way log of thing can be equal to log of thing is if those 2 things are the same thing. So it must be that x plus 1 squared over 16 is equal to 2. Does that look easier to solve now? Yeah, in fact, like, maybe you even see all of the moves from here on. Multiply that 16 over to the other side, take a square root to get rid of the square, because you have to remember there's a plus or minus that'll show up, and then subtract 1 from both sides. You buy that that'll work? So doing that all at once, I guess you'll get, well, doing a lot of it all at once, you'll get x plus 1 is equal to plus or minus square root 32. So x is equal to negative 1 plus or minus square root 32. And maybe you could know that the square root of 32 is the same thing as 4 root 2. Who cares about that? Let's ask ourselves, are both of those valid solutions to the original equation? So, let's see. Let's do a quick domain check. So let's see, I see an x plus 1 inside of a log. What types of things can I put inside of a log with them?
Positive numbers.
Positive numbers, only positive numbers. So x plus 1 needs to be positive. Do both of these numbers have x plus 1 being positive? The negative one seems bad, right? Because then x plus 1 would be negative root 32, but that's negative. So the domain is -1 to infinity. So only x equals -1 plus root 32 is a valid solution. How does that feel? Does that seem okay? With 2 remaining, I think what I would now like to do is I want you guys to have some time to do one of them, and then we'll come together and talk about, well, whichever one we want to. And I think, in fact, that I want only one of them to be done. Would you guys rather walk out 3 on your own or 4? Folks for 3? I see 3 hands. Folks for 4? 4 hands? All right, I guess 4 is ahead. Solve this equation, and then we'll come together and talk about it. And you can even talk to each other if you want to during this process. So if you guys come down to solutions or find yourself getting stuck, you can compare those solutions with other people, maybe even talk with other people about where you're stuck.
Turn this one.
Mhm. I thought that was just log base 34. Zero. That's why.
So I'm gonna apply the bottom.
Mhm.
And then
Oh, you're right.
and then just cut them off. But I don't know.
So wait, but foiling the line, did you just bring one of them over then technically?
So instead of writing it as squared, I just wrote it twice and multiplied, and then I just put all these to the left side.
Oh, okay.
Nice, so that was some, shows a nice increasing compensation and then it rolled back down, so that tells me that a decent number of people have made good progress. Do people want more time to like finish up their ideas before we talk together? All right, then let's jump right to the answer. What is the solution to this equation?
1 plus or minus the square root of 21 over 2.
Anyone get something different? So I think I want to take a quick moment and check whether both of these are valid solutions to the original equation. I'm not saying that either one of them isn't. I just want to make that sanity check. So square root of 21, that's like 4 point something? Maybe you know what it is more closely because you used a machine or you just know. So that's somewhere around 1 plus or minus 4 and some change, all over 2. So I guess that'll give you 5 and some change, all over 2, or 1 minus 4 is 3, then you keep subtracting. Negative 3 and some change over 2. And now let's think about domains. So I see an x plus 1 inside of a log, so what has to be true? What types of things can we see inside of logs? So x plus 1 needs to be bigger than 0. So what can you tell me about x? X has to be bigger than negative 1. I see here an x plus 2 inside of a parenthesis, so that means x plus 2 has to be bigger than 0, so x has to be bigger than negative 2. But that's the stronger condition anyway. So x has to be bigger than negative 1. Are both of those answers bigger than negative 1? No, one of them's too negative. That one, I guess, which came from the negative choice, so it has to be only positive root 21 over 2. So other than that detail, does anyone want the actual solution talked through it? Cool, let's talk through it. And lots of you have done it, so I think that there will be lots of opportunity for feedback. So it's not in log form yet. The left-hand side has multiple logarithms. Can you rewrite the left-hand side so it only has a single log?
Mhm.
Yeah. And in fact, I think we can do it in a single step instead of 2 steps. Where will this 2 wind up migrating? To the exponent. So x plus 1 squared, and those parentheses are important. And then I see subtraction. What's subtraction going to become? So doing it all in one step, you'll get log base 3 of x plus 1 squared all over x plus 2 equals 1. So those of you who wanted to see things walked out, was that too fast or was that okay? Okay. now we have an equation that's in log form. Yeah, right, it's literally log base 3 of thing is equal to 1. So I can rewrite it in exponential form as x plus 1 squared over x plus 2 is equal to 3 to the power 1, which is 3. I know that's like a rational equation. So, I don't know, the people who wanted to see this one done in more detail, do you want to see rational equation solved, or are you happy with this? More work? Okay, then I keep going. There's the equation you need to solve. Well, it's annoying that there's an x plus 2 in the denominator, so let's multiply that to the other side. And maybe I'll also FOIL out the x plus 1 squared. So I'll get x squared plus 2x plus 1 is equal to 3 multiplied by x plus 2, also known as 3x plus 6. Happy enough? That's a quadratic equation now. So I know exactly what to do. I'll put everything onto a single side and I'll use the quadratic formula. But I don't think I'll even use the quadratic formula. I'll just put everything onto the same side, giving x squared minus x minus 5 equals 0. And then make me appeal to the quadratic formula. Was that helpful? Okay. So one of the big takeaways is when you do these manipulations, if you lose a parentheses, then you'll screw up the answer. So it's really important that this was x plus 1 squared and not x plus 1 squared, because that square would just go away. Yeah?
Just, I guess a comment on the way I did it was I put everything in one, but yeah, it's going to end up being the same thing, because 1 is just log base 3 of 3.
Oh, yeah, absolutely. You could, at the first step, replace that 1 by log base 3 of 3. Yeah, there's more than one way to shake a stick. That's the saying. Nice. So, the next things that I want to do are some applications. So, radioactive decay. And I didn't take the time to pull up my own machine, so I'll rely on you guys to give me decimal approximations when the time comes. So if you have a radioactive substance, it will decay at a rate proportional to the amount of the radioactive substance present. And one consequence of that is no matter how much of a radioactive substance you have, it will always take a fixed amount of time for that quantity of that thing to become half of what it is now. But that length of time is called the half-life associated to that radioactive material. Different radioactive materials have different degrees of instability, and they break down into different sorts of particles, but I won't worry about that. I'll just worry, this isn't a physics or chemistry class. So I'll go straight to a model. If you do have a radioactive material, then you can model its quantity as a function of time by saying the quantity of this radioactive material after some t amount of time. Well, if it takes one half-life for it to reduce in size by a factor of a half, then if you want to know how much radioactive material is present after some amount of time, just count how many half-lives have gone by. So that t over lambda, that's exactly how many half-lives have gone by. Gesundheit. So there's a formula. Now let's try to use it. So U-232 has a half-life of approximately 70 years. I'm rounding like a fiend because I'm going to forget about this problem as soon as it's passed. If you're actually interested in a modeling problem involving uranium-232 and you care about the precision of your answer, look up the actual half-life. I think it's closer to like 67 point something years. So let's ask, if U-232 has a half-life of 70 years, if you start with 1 kilogram of U-232, how long will it take you to wind up with 1 gram of U-232? So let's try to set up this equation. We have a formula to use, a model. Right. The formula is the quantity as a function of time is the initial quantity times 2 to the negative t divided by half-life. And let's see what things are given. Do we know what lambda is? Yeah, what's the half-life of a U-242? 70 years. And I'll keep the units in play just so we see why the units walk out correctly. What's the initial quantity?
1 kilogram.
And it looks like the end result is in grams, so let's write everything in terms of grams. How many grams is a kilogram?
1,000.
That's a nice thing about metric, isn't it? Nice. So we can write this down. The formula we have for the quantity at any given time is 1,000 grams times 2 to the negative t divided by 70 years. And what quantity? We're interested in the time when the quantity is what? 1 gram? Right, that's how long will it take for it to get down to 1 gram? So let's set the quantity equal to 1 gram and try to solve that equation. 1 gram is equal to 1,000 grams times t to the negative 2 to the negative t divided by 70 years. So what would you want to do to solve this? What do you want to divide both sides by? So this is something different from the previous one. It's not a logarithmic equation at all, but it's almost an exponential equation, right? The only problem is that there is a 1,000 next to the exponent. So how can you get that 1,000 to not be next to the exponent? Divide by 1,000. So dividing both sides by, not even 1,000, but 1,000 grams. I want to keep track of the units. I'll see 1 gram. I'll keep the color coding, that's in green. Divided by 1,000 grams is equal to 2 to the negative t divided by 70 years. All right, well, let's cancel some things. Do you see anything that cancels or simplifies?
The grams.
Grams cancel. And that's nice because an exponent is only ever going to be just a number. And then I have 1 over 1,000. Maybe you would simplify that to 0.0001. But I'm sufficiently unconfident that I'll write down the right number of zeros after the point that I'll just leave it as 1/1000. Cool. Do we now have an exponential equation? What do we get when we rewrite it in log form?
Log base 2 of 1 over 1,000 equals -2.
Nice. Now what do you need to do to solve that for t? Multiply both sides by -70 would do the job, right? Get rid of the negative sign and get rid of the 70. So I see negative 70 years, but I'll put the years at the end. Log base 2 of 1 over 1,000 is years, is equal to the amount of time it takes. So how many people are upset with the way that answer looks? Yeah, why are you upset?
Because it's a negative.
It looks negative. There's certainly a negative sign out front. But is there really? What can you tell me about the log base 2 of 1,000? Of 1 over 1,000. What power do you need to raise? What type of power do you need to raise 2 to in order to get 1 over 1,000? a negative power. So what can you tell me about the log base 2 of 1,000? Say a power.
Be negative.
It's negative. So are you less upset with that negative sign now? Okay, well, let's appeal to our machines. Tell me, by using a machine, what is the log base 2 of 1 over 1,000? I think it's somewhere around negative 10. In reality, it's, but I want more digits than I can get by just thinking.
Negative
-9.966. That's enough digits for me. Because, right, the 70, I'm really only confident if in that up to a single decimal place. Ah, is that positive? Now you're less unhappy about that negative sign? Okay, cool. And then, well, right, now it's approximate. So we actually care about how many years we have to wait. What is that approximately equal to? Maybe say up to the tens and ones digit. Up to the ones digit. Up to the, how many whole number of years?
698 approximately.
Cool. So, if you know the half-life of a thing, you want to know how long it'll take for a quantity of radioactive material to decay down, you can set up this equation and use the things you know to solve it. Keep in mind that the end result will have to be positive. So if it looks negative, think about whether it is actually negative, because it had better not be. Everyone feel pretty good? So I think we have time to do one more similar to this before calling it for the day. Let's talk about radioactive decay and carbon dating. So, so how many people in here are either pursuing biology or archaeology or something adjacent? So you know that a really important way of measuring age of something, especially something organic that's old, is a technique called carbon dating, in which you take a sample of that thing, you measure the quantity of carbon-14, a radioactive isotope that's in that substance. You say, oh, well, the quantity of C14 in the atmosphere is roughly constant. It's continuously replenished by the fact that there is radiation hitting the Earth from the sun. And when an animal is living, it's continuously taking in C14 from the atmosphere. Once it dies, it stops doing that, so the C14 starts decaying. So that means that you can figure out how long dead an animal is by thinking about C14. C14 has a half-life of approximately 5,500 years. And so if you know, let's just do the example. If you have some animal, you know that when it died by knowing the mass of the thing and the density of C14 in the atmosphere, concentration of C14 in the atmosphere, if it starts with 4 grams of C14, you dig the animal up and measure that it now has 0.01 grams of C14. We can figure out how long dead the animal is. And how do you do that? Well, you just need to set up the equation. How much C14 is in the animal when you dig it up? That much. So Q of t equal to 0.01 should be the same thing as Q0 times 2 to the negative, that's wrong, 2 to the negative time divided by half-life. And we know the initial quantity. The initial quantity is 4 grams times 2 to the negative t divided by 5,500. And here I'm suppressing the units because all of the masses were in grams, and all of the times are in years. Does that look like an equation that we can solve using the same techniques as we just did? What do you think the first step should be? So it's annoying that there is a 4 on the right-hand side, right? How can you get the 4 to not be on the right-hand side?
Divide.
So 0.01 divided by 4. I guess that's 0.0025, but maybe you're happier with that anyway. Is the same thing as 2 to the negative t divided by 5500. Is that now an equation that is in exponential form? And the complicated stuff is in the exponent, so it's good to rewrite it in log form. You'll wind up with log base 2 of 0.0025 is equal to negative t divided by 5500. Is that now easy to solve for t? Yeah, I guess you just need to multiply both sides by negative 5500. So you'll get negative 5500 multiplied by log base 2 of 0.0025 is equal to t. And we'll put, as I said, we'll put the units back for the last step. Again, we have this issue that it looks like the answer is negative. There's a negative sign. But this thing inside the log is less than 1. So what type of number do I have to raise to in order to get a number less than 1? I have to raise it to a negative. So that log will definitely be negative. And by now I've stalled long enough that you guys can tell me what negative 5500 times the log base 2 of 0.0025 is. What is this approximately?
$47,549.
Nice. So, because you understand how carbon-14 will decay, if you measure the amount of carbon-14 that the animal has at the end, you can deduce how much carbon-14 should be in it once you dig it. And you can deduce how long it's been dead if you know how much carbon-14 it has in it now. Although, and I read this just recently, future archaeologists have been all screwed up by the fact that we did atmospheric nuclear weapons testing in the 50s and 60s, right? That's not a problem for, this generation. I mean, there's a separate set of problems for previous generations because of that. Cool. So, I'll pick up with some of these notes next time, and then the rest of next time will be about other applications of this logarithmic and exponential analysis. We'll talk about population growth and compound interest. Okay. Are you an on-campus kind of person?
I was going to
Okay.
see mom, dad.
Yeah, get back to your dorm room and try to get it back to me. I'll be here till at least 35 or close to
Get
the
back
wall.
up here.
Yeah, so bring it back to my office. If I'm not in there at the time, slip it under my desk and let me know. Yeah, thank you.
Don't tell me it's ready.
We have our quiz Wednesday, right?
That's right.
Yeah. Sounds good.
Thank you. Have a good day. You too.